All right, welcome back. This is Vibrations, and we are in week 1, and I think this is class 5. So I would like to explore a little bit the solution of the differential equation and its meaning. I believe I've already kind of did this in the previous videos, so you might want to skip over, but we'll check. So let's see. Recall that the solution to this will produce a natural frequency that is the square root of k over m. This is a really important thing to memorize, and you can see from these two write-ups of the solution how that substitution works right in there. And I added in here, I said, what kind of thing does that? And had solutions that are x as a function of time. Right, so its position as a function of time is going to be some magnitude. Often we use capital X for that. I'm not sure there's often some amount of switching back and forth between using like capital A or whatever right here. But here's the magnitude of the thing. And we're gonna, by the way, we're gonna ignore the phase angle. That's in there, but there can be a phase angle in there because you can start from a separate position. And we have now x dot, which is also going to change with time. And what you'll find is you'll go x times the natural frequency times the cosine of omega nt, and then x double dot with respect to time, x, whoops, going to be negative omega n squared. We'll leave that negative out a lot of times, so you'll see, but we're back to a sine wave. And if you were to replace these, let me take that back. Let me take that back. Let's replace these. Sorry. There you go. Right there, right there. Replace these, you'd have a negative x omega n squared sine of omega nt plus x. Oh, we have to put the omega n in there. I forgot the omega n. The omega n squared times x times the sine of omega nt. And you can see, and that it equals 0, that this is confirmed to be a solution right in there, right? Because we have all the same things over here that we have over there. So it does, in fact, equal 0. So this is like a proof that it checks out. You could also try, by the way, you could try x is equal to this guy right here, I omega nt. Right, so if you take the derivative of him, you get I omega n x e to the I omega nt. And if you take and do it again, you get I squared omega n squared x e to the I omega nt. And once again, if you put these guys and you plug them back up into here, you will find that you get, of course, that turns into -1. So you get negative omega n squared x e to the I omega nt plus x. Whoops, we have to put the omega n squared in there. I did it twice. Omega n squared, because that comes from right there, times x from right here, e to the I omega nt equals 0. And if we look at that, it's like, yes, it checks out. So these are important things to recognize. Now, let's see, in my pages here, I decided, so you also want to find, so I ignored initial conditions. So this first part of the thing, I ignored boundary conditions or initial conditions, I guess, initial conditions. So what if we have an initial condition? So the quite often the solution, instead of having this as a simple solution, we will take as what the people in diffie-qs will often write out as a times the sine of omega nt plus b times the cosine omega nt. And now we start to think of like, why does this thing move? If it's a spring in a mass, then well, why is it moving? Well, we must have done something to it. And it could either be that we have an initial displacement or we have an initial velocity. Because you could take the thing, you could just imagine, like without displacing it, somehow you magically set it in motion with an x dot downwards. So we could call that right there. Or probably easier to visualize is if you just pull it down a certain amount, and that's going to be initial in here. So we could have an initial displacement, or you could do both, by the way. Initial displacement, or you can have x dot. You have initial initial velocity. So at t equals 0, you could have xo is going to be, well, you place in that t equals 0, and right in here, you'll see that that's going to make the sine of 0 is 0, right? Did I say that right? Yeah, so you'd have a times 0, and then the cosine of 0 is 1. So you go plus b times 1. So therefore, we solve b is equal to x initial. And then we could also now add time there. We could say that x dot is going to be equal to, well, let's take the derivative of this thing. So we would have a times omega n times the cosine, right, of 0, because we're putting in the time of 0. So that's going to be equal to 1. And then we already know that this is equal to x0. I don't need to put parentheses around it. x0. But now this is going to be equal to, I should make this negative, right, because that should be a negative sign. Doesn't really matter. But the sine of 0 is 0, right? So therefore, a is equal to the initial velocity divided by the natural frequency. So we could get a more detailed solution. Let's make it another color, big old blue. A more detailed solution for the actual circumstances that we might want, that we would experience with a spring. So we would have x is a function of time is going to be equal to the initial velocity divided by the natural frequency times the sine of omega nt. And then you'll also have the initial position when this happens times the cosine of omega, the cosine of omega 10. Now I don't have this written down. Well, let me, boom. I don't have this written down anywhere, but there's equations that can establish what the phase angle. We can do a little bit of trigonometry identities here and mush these together and just make this the sine of omega nt plus some phase angle. And that phase angle will be a combination of these two coefficients. I'm not sure if this book does that. I haven't seen it yet, so but we'll be on the lookout for it. But we're coming up with some examples pretty soon. I think that's what's in the next video. So this is video 5. I think will be video 6 is coming up in a minute. Or after this. Talk to you soon.